So the span of a set of vectors in some vector space V is the collection of all linear combinations of those vectors. So if we have, say, v1 and v2 and da 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 up to vk, so some collection of vectors from V, then the span is going to be all of those things that can be written as a linear combination of v1 and v2 and so forth. So some choice of coefficients that will allow you to make that guy. So in other words, it's everything you can build. If you think of this collection v1, v2, vk as being types of Legos, then the span is going to be all the things that you could build out of those Legos if you were allowed to take as many of each different type that were in there. So that's what the span would be. Okay, so now the first thing to notice is that the span is a subspace. So we already saw this in the case of two vectors in a previous section, but it works no matter how many you have. So if S is any set of vectors in some vector space V, then the span of S is always going to be a subspace of V. Okay, so to see why that's true, we're going to have to check the closure properties. So let's start off by giving things names. So suppose that S, we'll call it by the same stuff here. So suppose it's these vectors right here, v1 through vk. And suppose we choose x and y as elements of this thing span S that we're supposed to check as a subspace or a vector space. Okay, so since we know that x is in span S, or since we've chosen x to be an element of span S, then that means that it's a linear combination of things from S. That's the definition. So it looks like AI, VI, some linear combination of the V's. And similarly, Y looks like some linear combination of the V's as well. So I can use any letter for the coefficient of Y except A, because I don't want to duplicate it, because then I'd be choosing the same element twice, and that would be no good. Okay. So let's see. So now I need to check the closure under addition and closure under scalar multiplication. So we usually do addition first. So if I look at the sum of these things, then I've got a formula for x, and it looks like this one, AIVI. And I've got a formula for y, and it looks like this one, BIVI. And it's a property of sums that I can, these are finite sums, so it doesn't matter how I write down the terms. I can write them in any order. So I can collect the coefficients of V1. And so I'd have like A1 plus B1, V1, and so on and so forth. I can collect the coefficients for all of them and rewrite the sum like this. And then I see that this one is some linear combination of the VI's where my coefficients are just the sums of the coefficients of the individual pieces. And similarly, when I do a scalar multiple of x, this is going to be C times this linear combination, which I can bring the C's in. Scalars are slippery. Put them wherever you want. And so this looks like the sum of a CI VI, where now the CI's are just C times AI. Okay, so that actually gives us the proof of this theorem. We're done. We get a box. Okay, so then you can ask, what kind of questions can we ask and answer using span? And so there's three questions we're going to look at. So the first one is, given a vector B and a set S of vectors, we can ask, is B in the span of S? So in other words, we're asking, is B something you can build using the parts in the kit S? All right, that's one thing that we can ask. And another thing we can ask is, given a set S of vectors, what is the span of S? What can you tell me about the span of S? A third question we can ask is, given a vector space V, can you find a set S such that the span of S is V? So can you find a collection of basic building blocks that are sufficient that they will allow you to construct anything in V? Okay, so in the subsequent videos, we'll look at each of these three questions individually.